Hi everybody, welcome to the 4.5 notes. We're going to continue to develop our ability to solve problems that are related rates, and we're going to work today specifically with the triangle model, which is one of the most popular ways that you'll see related rates. I would say the triangle model, and then anything with volume or surface area is when you'll normally see related rates. And so I'm going to read through the problem and then we'll kind of go through the steps that we learned yesterday. So a ladder 25 feet long is leaning against a house. If the base of the ladder is pulled away from the house at a rate of 2 feet per second, how fast is the top moving down the wall when the base of the ladder is 7 feet from the wall? So basically, I'm going to draw a picture first. There is a house. So here's my house. And then we have a ladder that's leaning up against the house. And the ladder, so this is the ladder. I'll do it in a different color. But the ladder is being pulled away from the house. So I want you to imagine someone pulling a ladder away from the house. This ladder is 25 feet, so that's good to know. And the base of the ladder is being pulled away from the house at a rate of 2 feet per second. So it's being pulled away at a rate of 2 feet per second. And the question is, how fast is the top moving down the wall? So how fast is this piece moving down the wall? So that's what we want to know. How fast is this moving down the wall? When the base of the ladder is 7 feet. So when this piece is 7 feet from the corner. So that's just kind of me trying to understand the problem a little bit. But I'm going to go over here to the side and just always list out the things I know and the things I don't know. And so to start off this problem real quick, I'm going to label some things. So I'm going to give all of these variables, and the specific variables I get, they'll make a little bit more sense in a second. So I'm going to label this A, this B, and this C. And so the things I know is that I know that the ladder at the time that I am trying to figure out how fast the top is moving down the wall, at the time that that's happening, the base of the ladder is 7 feet from the wall. So A equals 7 feet. B, I currently don't know what B is, so I don't know what that is right now. C, is this right here, and that's the ladder, and the ladder is always going to be 25 feet. That's not going to change. And then I am told that this base is moving away from the wall at a rate of 2 feet per second. So that's a rate, and so that's going to be dA dt. That's how how that length A is changing with respect to time. That's changing at 2 feet per second. And then the question is asking me, how fast is the top moving down the wall when the base of the ladder is 7 feet from the wall? So what I'm trying to figure out is how this right here is changing. So my end goal is to find dB dt, and that's what I don't know. So this is my end goal. So now I need to think about, okay, well, what is something that relates, what is an equation that relates these three sides? This is going to be a right triangle. You would build a house at a right triangle. You're not going to build your house like at an angle or anything. So we're going to assume that that is a right triangle. And so if that's a right triangle, the reason I use the variables A, B, and C is because if that's a right triangle, the thing that relates all three of those sides is the Pythagorean theorem, which is A squared plus B squared equals C. So that's the thing that relates all three of those sides. But that equation has nothing to do with rates right now. But if I take the derivative of both sides, it will have to do with rates. That will tell me how each side is changing with respect to each other. So what I'm going to do is I'm going to go ahead and I'm going to take the derivative of both sides. But before I do that, one thing that I can do is I know if I look at this equation, A is changing, right? Because the ladder is being moved away. B is changing, so because the ladder is being moved down, right? But the one thing that's not changing is the ladder is never changing, right? And sorry, I wrote this equation wrong. It should be A squared plus B squared equals C squared. The ladder is never changing. And so I actually can take my equation and know that C squared 25 squared, that's going to be a constant. That's not going to change, and so I can go ahead and plug that in now. So now what I'm going to do is if I want to try to help myself find some rates, I'm going to take the derivative of both sides with respect to time. With respect to time. And what that does for me is the derivative of A squared with respect to time is 2A times dA dt. The derivative of B squared with respect to time is 2B times dBt. I'm just using my implicit differentiation strategies. So I'm just viewing every one of these functions as a function of time. I'm taking the derivative of the outside and then the derivative of the inside. So I'm basically viewing a squared as a to the t power squared, taking the derivative of the outside and then the derivative of a with respect to t is d a dt. And then 25 squared, that's a constant. Even 25 squared is 625, but I don't even need to know that. I know that's a constant, so that's going to come out to be 0. And so my end goal here is to solve for dB dt. So I'm going to plug in the things that I know. I know that a is 7. I know that dA dt is 2. Now, one thing I want to clarify is this is a positive 2 feet per second. And so sometimes it's going to be hard to know, like, okay, are things negative or positive? But because it is moving away, that makes it positive because that's moving away, basically away from that right angle because it's moving away from the model. It's positive. If it's moving towards, it's going to get negative. So away is positive, towards is negative. Then 2, and I'm going to plug in B. So notice I don't actually know what B is. So I actually have 2 unknowns here, which kind of gets me stuck because you can only solve when you have 1 unknown. But we should be able to find B, right? Because we know that this side length is 7, this side length is 25. So we can just use our normal Pythagorean theorem equation to find that. So I'm going to do that over here. I'm solving for B over here. So I know that A is 7, so I'll have 7 squared plus B squared plus 25 squared. 7 squared is 49. 25 squared is 625. If I subtract that on both sides, I'd get 576. And that makes B plus or minus 24. But, we don't want to work with 24, right? We're just going to work. We wouldn't work the negative 24. We'd only work with positive 24 because this is time, or this is distance and lengths. So then I'll put 24 here. So now I'll just clean this up. 2 times 7 is 14. 14 times 2 is 24. 2 times 24 is 48. And then I'll just do some normal solving. I'm subtract 24 on both sides. So I'll get 48 dB dt equals negative 24. And then if I divide 24 on both sides, that will simplify down to negative 7/12 feet per second. So I just divided 48 on both sides and then I simplified. And so this is my final answer right here. dB dt equals negative 7/12 feet per second. Notice that comes out to be a negative rate, which makes sense because the distance, so this is moving, this ladder is moving down, as it gets pulled out, right, it would be moving down. And so the distance of B, the length, should be getting smaller. It is changing at a rate of negative 7/12 feet per second. It shouldn't be getting bigger because the length between the top of this ladder and this right angle is getting smaller. And so that's why away is positive, right? Because if I move this away, this is getting bigger, and towards is negative because if I move it down, this length right here is getting smaller. So that's how you do one of these problems. You are almost always using the Pythagorean theorem. There are going to be some problems, and maybe I'll give you some challenge problems where you're using trig, but normally you're going to be using the Pythagorean theorem. So let's do another one. They're all going to be a little different because different things are going to be moving. Your pictures are going to be a little different. But we have an automobile traveling a rate of 30 feet per second, and it is approaching an intersection. When the automobile is 120 feet from the intersection, a truck traveling at a rate of 40 feet per second crosses the intersection. The automobile and the truck are on roads that are right angles to each other. How fast are the automobile and the truck separating 2 seconds after the truck leaves the intersection? So I hear the word intersection a couple times. So what I'm going to do to draw this picture is I'm going to start by just drawing a little intersection. This is my mini intersection. And so first, it doesn't tell me what direction things are coming from. Sometimes it will be oh, the automobile is coming from the north or from the south. So pay attention to that. But this time it doesn't say anything. It just says first an automobile is traveling at a rate of 30 feet per second and it's approaching an intersection. So I like to draw these with arrows, but I have this automobile. Pause.
Please pardon this interruption. At this time, if Dr. Crow, Ms. Letitia, and Ms. Matt, third period classes, would get their coats and make their way out the door for the field trip. Again, Dr. Crow, Ms. Letitia, and Ms. Matt. Thank you.
Okay, sorry about that. But basically, we have this automobile, and it's traveling towards an intersection at a rate of 30 feet per second. And then we're going to be concerned about what's happening here when the automobile is 120 feet from the intersection. So I'm going to write 120 feet. That's like the moment in time we're concerned about. And then it says a truck is traveling at a rate of 40 feet per second, and it actually crosses the intersection. The automobile and the truck are on the roads that are on right angles to each other. So that means that the truck has to be on this road, and it says it actually crosses, and so it's going to be going like this. And so that's our truck. And this truck is traveling at a rate of 40 feet per second. And then it doesn't say like at the time it is, right? Yeah. Now, one other thing we need to consider is, do one of these need to be negative, right? And so the answer is yes. Try to think about which one it would be negative, but the answer is going to be this one, because this one's getting closer and closer and closer to intersection, so its distance from the intersection is getting smaller, and so that's why this one is negative. And then this one's going to be positive because it's moving further and further away from the intersection, so that its distance is getting positive, so that would be a positive one. So this is going to make a triangle right here, and the question is asking, the automobile and the truck are on roads that are at right angles to each other, how fast are they separating? So what we're trying to figure out is, I'm going to call this C because it's a hypotenuse. We're trying to figure out how fast they're separating. So what is this distance? So overall, let's talk about this. This is going to be called A, this is B. So A is going to be the automobile, and A is currently 120 feet from the intersection, so that's what it currently is, right? But it does say how fast are the automobile and the truck separating 2 seconds after the truck leaves the intersection. And so it's 120 feet from the intersection when the truck goes through the intersection. But now we're 2 seconds later. And so what is the distance the car is from the intersection 2 seconds later? Well, it says it's moving 30 feet per second. 2 seconds have passed. It was at 120 feet. Now, 2 seconds later, it's lost 30 feet per those 2 seconds. And so altogether, the automobile is actually, at this moment that we are concerned about, the automobile is 60 feet from the intersection. DADT doesn't change. It's still driving at this rate of negative 30 feet per second. B, we know is, we don't know currently. Well, we can figure it out, right? So at the intersection, that's when the truck passes. 2 seconds have passed. It's moving at 40 feet per second. So that makes B be at 80 feet at this instant that we're concerned about. DBDT is 40 feet from the intersection, or is moving at a rate of 40 feet per second. And then our end goal is how fast are the automobile and the truck separating. And so our end goal is to find DCDT. And again, we're going to use the Pythagorean theorem to do this. So it'll be a squared plus b squared equals c squared. Pause for a second. Okay, well, we're just going to keep going.
Please pardon the interruption. At this time, if Miss O'Connell and Miss Seifert classes could dismiss for the field trip. Again, Miss O'Connell and Miss Seifert classes. Thank you.
Okay, so taking the derivative of both sides with respect to time, I'll get, and these are always going to come out to be the same thing, so you can like basically memorize it. Equals 2c times dc dt. Another shortcut you can basically do here is like notice that there's a 2 in all of these, so you can essentially just like cross out all those 2's because you could just divide every side by 2. And now I'm going to plug in things so I can solve for dc dt. Real quick though, I don't know what c is, right? And I need to know what c is. I have enough information to figure out what c is because all I have to use is the Pythagorean theorem to figure that out. So I'm going to do c down here. To find c, I'll do 120 squared plus 40 squared, and that's going to equal c squared. So, oh, sorry, I plugged in the wrong numbers, sorry. I'm supposed to be using where they are at the intersection. So 60 squared plus 80 squared equals c squared. 60 squared is 3,600. 80 squared is 6,400. That equals c squared. That comes out to be 10,000 equals c squared. So that would mean that c squared equals 1,000. I'm going to check that real quick. Or is it 100? It's probably 100. 1,000 doesn't really make sense, does it? Yeah, it's 1,000. Or it's 100. Okay. So c equals 100. So now I can go ahead and plug everything in. So a is 60. dAdt is negative 30. B is 80, dBdt is 40, C is 100, and then we're solving for dCdt. So this is a negative 180. 80 times 40 is 320. But add a 0 to both of these, sorry. And then 100 times dc dt. This gives us 1400 over 100 dc dt. And then I would divide that both on both sides, and that would give me 140 feet per second, which is what dc dt is. So that means that the automobile and the truck are separating at a rate of 140 feet per second. And that makes sense for that to be positive, because this is just going to be getting bigger, because this is moving. The truck is moving quicker than, the truck is moving quicker than the automobile is, so that makes sense. So, okay, let's do a couple more. Let me look at which ones I would rather do here. Okay, I want you guys to try this one on your own, okay? I want you to try one on your own, and then we will do one more together. So try this one alone, but I want to tell you guys that the answer to this one is going to be 57.6 meters per second. I want to see if you guys can get that by yourself. Okay, I actually want you to try the next 3 problems on your own. So it's okay if you can't figure it out completely, but I'm going to give you the answers. And so I want to see a good attempt on all 3 of these next ones, because they're not really that crazy different than the ones that we just did. So example 3 is 57.6 miles per hour, or meters per hour. Sorry, meters per second. The next one, example 4, is 420.084 miles per hour. And then the last one is 11 feet per second. So I want to see your best attempt. Try your best. You got this.